Okay, we're going to record here. This is the Wednesday lecture for Physics 211. I'm going to talk about sections 1.4 to 1.7 today. Hopefully, we don't have any issues, and I have to do this in 2 videos like I had to do on my other classes. So let's just rock and roll and get going. 1.4 velocity. Velocity. So speed, and we talked a little bit about this the other day, but I want to make sure we get it. Speed, we can say, is distance traveled over the time elapsed. I'm going to Myrtle Beach. That's where everybody wants to go, right? Go crazy and everything, right? So you're in Myrtle Beach, I don't know, 300 miles, let's say. If I can do it in 5 hours, that means I average my average speed. Let me put average here because this is average. My average speed, 300 miles in 5 hours, is 60 miles an hour. And that would be really good because then you've got to take at least one pee break or something, right? Get some gas maybe or something like that. Now, that's speed. Speed is how fast you're going. Velocity, as I said the other day, is how fast in a certain direction. Velocity then, since it's got direction and magnitude, is a vector. Speed only got a magnitude, is a scalar. Very good test question could be, why can a cop not give you a velocity ticket, but can give you a speeding ticket? Okay. We'll talk a little bit more about that next time. Just the way you would write this, you have to say 60 miles an hour, 60 miles an hour. If you go to Myrtle Beach, you'd be going southeast from here to here. Okay? That's the way you would write it. Now that's velocity. Let's look at acceleration. In this case, linear acceleration. If you want to think that speed and velocity is fast or fast in a certain direction, if you're accelerating, you're going faster. If you're throwing your brakes, you're going slower. You're reducing your speed. Acceleration is the rate of change. For all of you that have calculus, when I say rate of change, you know that means derivative. So we can do derivatives with this later on. Rate of change of the velocity. Fast, you can think velocity. Faster, acceleration. Slow, the there means something's changing. And that change, if it's for acceleration relative to velocity, that's acceleration. That's acceleration. Now, how can you change acceleration? Acceleration occurs when you speed up, increase the magnitude of your velocity. You slow down, you decrease the magnitude of your velocity. Or what? Remember, velocity is a vector. To accelerate is the rate of change in velocity. If velocity is how fast you're going, and we're changing how fast, there's one more here. One more way to accelerate. Because we didn't take into account direction. So you can accelerate by changing your direction. Change direction and accelerate. Yes, Dr. Knight? Maybe not. But the way we define acceleration and velocity, it does. And later on, when we talk about forces, because Newton was one kind of developed all this theory initially anyway, you'll see how for there to be forces, there must be an acceleration. And changing direction is part of that understanding of what's called circular motion and understanding centripetal and centrifugal type forces, centrifugal forces. All right? So you're saying, all right, that's not making sense though. That's whatever. Well, let's look at it. In a car, or a car, what makes your car speed up? You step on the gas pedal, right? What's the fancy name for a gas pedal? Speed up. Step on the accelerator. Step on the accelerator. That's why it's called the accelerator. It's the go fast button, right? Most of these are pedals. If you got a new vehicle, or your parents have some fancy car, these are actually, it's like fly-by-wire basically. It's just a button there, and force on it and stuff translates to how much it increases. A lot of older type car systems, there's a I'm saying a chain, but basically there's linkages to that, and that opens up the carburetor and changes something on the fuel injection system. Slow down. What if the car slows you down? Well, you can take your foot off the accelerator, and the car would slow it down itself. The engine would slow itself down. But generally, when you want to slow down, you step on the brake. Step on the brakes. So the brakes make you accelerate. The brakes make you accelerate. What can also be used to change? How do you change direction? Well, you can get hit by another car and that'll change your direction. Grab the steering wheel. Turn the steering wheel. So the steering wheel changes the direction of the car. So what have we got? You would normally tell me your car's only got one accelerator. In common vernacular to the average person out there. But you're not that. You're a physicist now. You're an engineer now. You want to study those things. You want to go in that direction. You know the car doesn't just have one accelerator. It's got three. What are those three? The accelerator, the brakes, and the steering wheel. All of those are accelerators. And that seems like a good test question. Okay. All right. Let's look at the equation for this. For acceleration. Put this in terms of the way the book does it. So they say acceleration is the change in velocity over change in time. Or if we want to write fancy symbols, A for acceleration, the arrow on top signifies it's a vector, delta V over delta T. Where time is not a vector, it's a scalar, because time only goes in one direction, and velocity itself is a vector, and that signifies it. Now, one thing I do want us to note, this is the average acceleration. That's between some initial and some final time. Because we know delta T is T final minus T initial. We only have data for this because we have the initial velocity and the final velocity, initial time and final time. If we want to write this out, I could say this is V final minus V initial over T final minus T initial. I only have data when I would put numbers in between these two. So in between the initial velocity and the final velocity, could it be slowing down like a rabbit? Could it be going slower as a tortoise? And then at the end, jump real fast? I don't know. But I can find the average. Average is tells me what it is averaged over all that time that we took our data across. Okay? That's why it's called average acceleration. So let's think about it. One thing I do want to do, if you're speeding up, your velocity vector is the same direction. It's going faster than your acceleration. And your acceleration vector. If you're slowing down, your velocity vector is in the opposite direction. As your acceleration vector. Why is that in the opposite direction? Well, the book shows it graphically, and I want you to look at what the book does, but I want you to think kind of visual in your mind, think of a real object. Because we're going to relate accelerations to forces here in the next few chapters. So if I'm moving along my velocity, I'm okay, and I slow down, what can make me slow down? Well, somebody hits me in the chest right here. They kind of push me back this way, and I'm going to slow down. Now, if it's a little kid, you're going to slow me down a little bit, right? I'll just take care of it, right? Or a bug or something like that. Now, so it's pushing me back. Now, if I'm doing this way, I want to go faster. Say somebody kicks me in the back. I'm going to go forwards. Now, so my velocity and my acceleration in the same direction when I speed up. But my velocity and my acceleration are in the opposite direction. This is velocity. This is acceleration. When I slow down. Okay? When I slow down. And we'll talk about changing direction and that stuff a little bit more later on. Okay? The author does a lot of stuff with motion diagrams and explains that. I'll just say here, example 1.4 is good. I want to look at example 1.4, put that in your notes. That's basically looking at a motion diagram of a spaceship landing on Mars. It's a good basic one. I do want to get a little bit to position versus time graphs. So we're going to start using position versus time graphs. Then I'm going to talk about solving problems. This is section 1.6, motion in one dimension. Motion in one dimension. One dimension means straight line, okay? Basically, straight line. But you tell me, we don't move in straight lines, we move zigzag, right? We curve around and stuff. We are crawling. We're rolling around, we're not even crawling yet. This is the baby of the baby steps in physics, okay? We're sitting around doing goo goo gaga and maybe turning on our back or something with this. We got to start somewhere. And that's what's up. As we go on, we'll get to changing in motion and stuff like that. We'll start crawling. We won't run in this course too much. We might jog a couple times. But we got to get the basics down. And that's why we're starting out here. Okay. So in a straight line, one of the ways we represent motion in a straight line is a position versus time graph. Now, I know you've seen graphs. I didn't like them, some do, some don't. How do you know what goes on X? How do you know what goes on Y? That was a question I always had. I never really got a good explanation. They would give me an answer, but no one really made one that clicked because I couldn't see it. So when you want to think about this, I will tell you, of course, whatever's first goes on the Y-axis. Whatever's second goes on the X-axis. Okay? So when you do a graph, if I say a position versus time graph, I'm going to have time on my, put that in seconds, on my X-axis, and I'll have position, we'll put that in meters, that's my unit, on the Y-axis. And we'll keep going here. We normally stay in the first quadrant because it's easiest. It doesn't matter. We can stick it wherever we want. We choose a coordinate system wherever we want. Since we can do that, try to make it so you stay in this quadrant where these are most positive if you can in these directions. We'll do some down below here. We can't do negative time too much. You can do it relative to a point in time. You can do what happened 10 seconds earlier. But if we make that our initial point that we just base everything else on, we're really just going to use this first and fourth quadrant. Okay? Now, how do I know which is which? Whatever's on your X-axis is your independent variable. Independent variable. What does independent variable means? If you're, what was the Rudolph the Red-Nosed Reindeer? Maybe you saw it, maybe you didn't. You know, when the guy wants to be a dentist, says, "I'm independent." And Rudolph does the same thing. "I'm independent." And then I think the monster knocks him down or something like that. Now, the Bumble, that's what I call it, the Bumble. One guy did. You call him Cornelius, call him the Bumble. Now, if you're independent, do you need anything or anybody to depend on? Can you take care of your complete self? If you're independent, you can pay your bills. You can pay your own insurance, pay for yourself. You can get your own food. You can provide your own house. You know, you're independent. And if you're independent like that, parents be pretty proud of you. You know, they'd be grandma, relatives. He's independent. She's independent. She's making it on her own. That's cool. That's what we hope that they would do. Independent variables don't need anything. They're what you start with. Okay? And what the problems we do and the things we're interested in, we're going to say, as something changes, but when this occurs, what does it do to something else? Okay? If this occurs, what does it do to something else? You're going to think of, in this case, in time and position, time is going on, time marches on. I want to see how my position changed over that time when I walked across the screen here. And I can do that. Now, with what I'm doing here, what would that look like graphically? What would that look like graphically? Oh, by the way, let me finish up. My apologies, I went a little too fast. Your y-axis is always your dependent variable. If you're dependent, many of you probably haven't done your taxes yet. Your parents probably make you a dependent. What does that mean? That means that you depend on them for food, for housing, for shelter, for money maybe. Get your money out. You could. But if you're a dependent, something else is causing you to happen. Something else is causing something to happen. All right? That's your y-axis. So when you look at a situation, what's starting it all, what's causing it, and what's the reaction? You can almost call it like this. Your x-axis is the cause. Your y-axis is the effect. Okay? So when I ask you to do graphs in lab, I'm going to put just give me a velocity versus time, give me a voltage as a function of time, or I don't know, energy as a function of position graph. I don't know what to put on what. Well, one, I told you there, first and second. Or you can look at the situation where I really don't tell you, I tell you make a graph and prove it. And you're going to need to think which one's independent, which one's dependent. And look at that situation and think out which one's the cause, which one's the effect. And that will help you out to know which is which. Okay? Now let's get back to that situation. I'm walking across like this, constant velocity, pretty much. What's my position versus time graph going to look like? Something like that. Why? Because my position, I can put numbers here. It's, 0.2, 0.4, whatever, 1, 2, 3, 4 seconds, whatever. It will look something like this. We're going at a constant velocity. So what if I did this? What would that look like? Okay, so I start out, I put more dots, and decent. Then that slope's going to change because I went a little slow for a little bit of time. Then after going a little slow for a little bit of a time, I sped up. It would look something like that. That would be what the graph would look like. Not that I would give you a lab like this. Maybe that's next week's lab. I haven't decided yet with that. Understanding graphical, understanding emotion is actually a very important part of physics, a very part of understanding. And you're going to see graphs the rest of your career. Either if you're computer science guys, you're still going to see graphs, especially in engineering, you see graphs all the time. Understanding how to analyze graphs is very important. Okay. What if I did this? What would that look like? Well, since that's a rhetorical question, because you're not here, you're watching a video. And we go up, 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 up. Because my position is increasing over time. Now, over a certain time, my position doesn't increase. I'm staying where I'm at. And then I go back to where I started. So my position has to go back down. Okay. That would be my position versus time graph in this situation. Okay. That might be important to know. Graphical understanding of motion. Okay. Let's look about solving problems in physics. This is extremely important. Solving problems in physics. I will give you a technique to solve problems in physics. It's similar to what is in the book. You will choose whether you want to use that technique or not. Those of you that don't choose it have a higher probability of not doing well versus those that do choose to do things or in a similar fashion the way I ask you to do. We're all adults. You're 18 or older. You're an adult legally, so you can choose whether to solve a problem this way. I will tell you this, especially if you're computer science, or if there's any biology type majors or chemistry majors, who tend to just want to do things and get out and be done. You might be able to get away with it part of this semester, not get away with a lot of this semester. If you're taking a second semester, that ain't going to work because you can't conceptualize those problems in electricity and magnetism like you maybe can do in your head here. It's up to you. If you want to increase your risk of doing bad, ignore this part of the lecture. If you want to increase your probability of doing good, maybe you should try out this technique. It takes more time, it takes more writing, but odds of getting a better grade go up immensely. All right? So to solve problems in physics, what's the first thing you do? Get an equation, right? Get an equation. That's what you math were taught. We got to get our equation sheet out, find an equation. As soon as we read the problem, we find the equation. If you were taught that, you were taught wrong. To be honest. It's not what you do. You probably weren't taught that. But that's what you do. You're probably doing it wrong. Well, it worked for me there. Just because it worked there doesn't mean it ain't going work, doesn't mean it's going to work here. Okay? Those of you doing sports, you're stepping up a level. You realize you got to have better fundamentals. You understand, you might have done physics in high school and did well there, but this is college, and you need better fundamentals. Okay? Problems get a lot harder. All right? So let's have some good fundamentals here. First thing I want you to do is draw a picture. Draw a picture representing the situation. First thing I want you to do is draw a picture representing the situation. All right? Does it have to be fancy? No. Some people go overboard and spend 10 minutes drawing a picture. Okay. That's 9 minutes you could use for something else. You will see, I will draw stick figures. I will do very, very basics when I draw pictures, okay? Just draw the basic picture so you can get a general understanding of what's going on, okay? When it gets fancy, maybe you do other stuff. But just use basic representation. Don't draw people, bobcats, ants, or dung beetles. Draw a point, or maybe a circle or a rectangle or a blob, okay? Just make it easy on yourself. Second thing, determine your coordinate system. Position. That's your X and your Y. Really, the thing here you got to know is where is 0? Where are you going to put 0 at? I will say wherever easiest, I think that's right, to solve a problem. Also, the Fix had a song where you guys were born, you don't care, called Saved by Zero. Don't do your coordinate system right, I should say. Don't do your coordinate system right. It can mess you up. Putting a 0 at the easiest place will save you a ton of work going forward. How do you know where to put it at the easiest spot? Experience, honestly. Use what you see a little bit. Put that coordinate system in there. After you've drawn your picture, put your coordinate system in there. This is real important. Now you do the equation, right? Yeah. After you do that, list your knowns and your unknowns. A lot of times with unknowns, it's not always, but it must include what trying to find. What are you trying to find? Okay? What are you trying to find? List your knowns and unknowns. And label them well. I will say label well. And if you do this, you can, put on the picture. You drew a picture initially. Well, if the velocity is 20 meters a second, and you got a car, you could write above the car, velocity v equals 20 meters per second. That way it helps you see it better. If it makes it too complicated, don't. But I'll do that a lot. So I know when I look at this car, how fast it's going, its acceleration, maybe its position. Okay. List your knowns, draw a picture, determine the coordinate system, find your 0, list your knowns and unknowns, and then now look for relevant equations. Equation or equations. There are more than one-step problems in physics, okay? There'll be many problems where you'll find one thing, and then from that, you use it to get the answer you're looking for, okay? Those are 2, 3, 4-step problems, or something like that. 4 is pushing it. Most of ours are 1, 2, 3-step problems in general. Now look for your relevant equations. Did I say to get a calculator out and plug it in yet? No, I did not. Once you determine the relevant equation, you're going to have lots of equations to go through. 5. Now, I'll say plug and chug. And that doesn't mean typing into your calculator, your fancy dancy TI 86,000 calculator you paid $1,500 for, right? That can do everything and wash your dishes. Okay? No. Do you need a big fancy calculator for class? No. Can you use an app for a calculator? I don't care. Maybe you want to use one of those TI calculators. It's old tech. Do what you want. You got to be able to do the calculations. But plug and chug here. Now, you're thinking I'm saying plug and chug all in your calculator. The answer in your calculator is last here. Write it down first. Once you wrote down the equation with the variables in it, then pull your calculator out. Or your device, your calculation device. Some of you may think you get here. Who knows? All right? But write the things down. Write the equation down. Write the velocity equals 20 meters per second. Put that in parentheses. And then right beside it, parentheses, put 5.0 seconds. And then, of course, we're going to have that equal position, but x equals that there. And then underneath it, then write down x equals whatever you get for your output. Okay? Write more on paper. The more you write on paper, I'll be honest, when you do these problems, the easier they'll be and the more you'll retain the information. The less you write on paper, and the more you do in your calculator, and the more you do in your head, the harder class is going to be, and you'll get more stuff wrong. Maybe you're super smart. Maybe you're much smarter than me. Maybe. I've met people smarter than me. Not many, just a couple. I'm kidding. Some people can get away with it. Maybe you can get away with it at this level, but you're not going to probably be able to get away with it at higher level. There will be a point where taking shortcuts will sooner or later hurt you and set you back. And that's when you really got to start changing your ways. Honestly, in my academic career, from going to high school to college initially, God, it was so hard initially. I was on a quarter system back then. My first quarter especially, even the second quarter was trying to figure it out. My third quarter, I had school figured out how I had to study and make things work. I was able to rock and roll. When I went to grad school, I tried using undergrad techniques and ways of studying. I messed up big time on my first test. I flunked my first test in grad school. And by the way, 1 F in grad school, the program I was in, you were gone. We only had like 4 tests in that class total. Professor and I had a little come to Jesus meeting, and I realized I need to come to Jesus and figure out how to study better. And I changed my way of studying. Okay? You're going to have to do that. Right? You're going to have to probably change your ways if you develop any bad habits in high school. Okay? Now, for many of you, last thing you get an answer, you go on. That is not the last thing you do in an engineering or physics curriculum, because here, this isn't math. I'm not throwing off on math, but numbers mean something. It means something in math, and they're just, in general, looking for the numeric values. Here, we want to see if it actually is a reasonable answer. So 6, which I'm putting out there, here, all right. So I would say, last thing to do, when you do your answers, when you calculate an answer, check for sanity. Do a sanity check of your answers. If I give you a problem with a car and it's going, from 40 miles an hour to 60 miles an hour, and I say in 2 seconds, and I ask you what the acceleration is. If you get an answer in the millions, it's wrong. I don't care what your calculator said. It's wrong. If you get an answer decimal 0.0005, 2, 3. It's wrong. You can't accelerate that slow. Can you even, 2 seconds, your acceleration is 0.005? No, it's too small. 1,000, a couple of thousand in 2 seconds? No, it didn't change that much. Check for reasonableness, okay? That's important. Because you're going to get answers, you're going to do these problems, and when you do a sanity check, you're going to get an answer. If you're just trying to get an answer, which some of you are trying to do, which some of you have done before, when I'm giving partial credits, and you got an answer that's cray-cray, very little partial credit is going to be given. Now, if you got an answer that's in the ballpark, what it should be, because you looked at this, and I can tell, well, they looked at it and they erased it, or what they've got, I can go back and see where they made a mistake. If it's a ballpark answer, you got a lot better chance of getting good partial credit. Okay? Because I know you're close to it. You're close. This is a process, okay? Do a sanity check. Okay? How to solve problems in physics. If you guys will follow these, guys and gals will follow these 6 steps, I promise you, from teaching physics for, I taught this course, courses like this, for about 15 years. Taught labs for this course, probably close to 20, including the course. I taught labs a bunch in grad school. This works. It's a technique that works. Now, if what you want to do works every time, go for it. Just better work every time. Okay. If it doesn't, maybe you will consider using this technique. Okay. Friday, I'm going to start on 1.8, units and significant figures, and chapter 2. So you want to read a little, start reading on those sections, start reading the first couple sections of chapter 2 and 1.8 on Friday, and we'll rock and roll it. All right, thank you.